Okay, so this is our first problem in working on trying to find values for internal shear force and bending moment. This particular problem is interested in a section at C. Now, if I were to cut the structure at C, do you want to look at the left side? I'm sorry, the left side or the right side? Left? Let me do it again. I'll draw, maybe I do there. So there's my line. Left side or right? Left, right. If I did use the left side, what do I have to find first to get started? I got to find all my reactions. If I do the right-hand side, do I have to find any reactions? No. So what do you think? I'm all about minimizing effort, so I'm going to go right. Not in politics, just in this thing here. Now, we have something that's a little odd here. There's a point load right at C. How do I cut a point load in half? Can't. So I'm going to have to cut this structure just to the left of C, and then we'll look at it just to the right of C. And I will see if we see any differences. You guys see what I'm talking about? So let's do the first one. I'm going to say let's look just to the left of C. So if I draw my free body diagram, since I'm just to the left side, then that 500-pound force at C is there, right? And then I have the next one at point D. And then I have the last one at the cantilever. And of course on the free end I have an applied couple. It's 2 kips per foot. I'm going to change that to 2,000 pound-feet. And now I'm on this side. Which way is positive axial force, right or left? It's this way, right? Which way is positive shear, up or down? Up. Why up? Because it's going to try to force this edge to move clockwise. See that? And then, of course, I've got my moment, which is positive there. So I'm going to start, just to remind you, I'm going to put little plus signs as superscripts to let you know, to remind you that that's the positive value, the positive sign condition. So now with that said, I'm just going to use equilibrium and make sure this structure is in equilibrium. So the easiest place to start will be to sum moments at the cut we just made and make sure it's in equilibrium. And again, I'm using right-hand rule. So I'm going to sum moments right there. And of course, at that point, the axial force and the shear force create no moment. So I have just the moment. Now, with my sign convention in statics, is this a positive moment or a negative moment? It's a negative moment, right? Does this first 500-pound force create moment at C? No. If it did, it would be almost negligible because the moment arm is so small. But these other ones do. And those would also be negative. So I'll have negative 500 pounds times a moment arm of 10 feet minus 500 pounds times a moment arm of 10, oops, sorry, I almost messed it up, 20 feet. And then the applied moment at the end, according to my sign convention, is that positive or negative? It is negative. So that'd be minus 2,000 pound-feet. So I can solve for the moment. Looks like I get, what's that, 5,000 plus 10,000 plus 2,000, right? That's 17,000 pound-feet. That sound right? So I'll go ahead and change that to kip. So that'll be 17 kip-feet. And it's negative. Does it make sense to you that I have a negative bending moment at C? How do you think this beam is going to behave under these load conditions? It's probably going to bend something like that, right? What does that look like to you? Does that look happy? No, it's kind of half a frown, right? And we know that kind of shape is negative bending moment. So that seems to match. So I'll put a little check there because it seems like it matches my intuition. Yeah.
This was the right of the beam, right?
This is the right section, but this is the left side.
Got it. Okay.
So now I can sum forces. So I'll sum forces in the y direction. And what do I have left? I'm using up as positive, so I've got a shear force going up. I've got 1, 2, 3 forces going down. Those are half a kip. So what is the shear equal to? Looks like it's going to be 1.5 kips. And just to be complete, I'll go ahead and sum forces in the x direction, but in the x direction I only have the axial force. So there is no axial force in this beam. Okay? And again, that was just to the left of the structure. So what happens if I go just to the right? So my free body diagram looks exactly the same except for this force right here, because now I'm on the right side of C, so I don't apply the 500-pound force. Everybody see that? So I'm going to redraw my diagram. So that force at C is over here on the left body, but I still have my 500-pound force in the middle and at the end. And of course the applied moment. So on the left side, I still have a positive axial force that I'm interested in, positive shear force, and there's my positive bending moment. So I'm going to apply the same strategy I did to the first body to the second body. So let's see what changes. So I'm going to sum moments at the cut and make sure it's in equilibrium. So again, summing moments here, I've got this moment at the cut. That's a negative moment. I've got 1, 2 moments due to these 500-pound forces. They're also negative. So the first one is 500 pounds is the force, and the distance is 10 feet. The second one is 500 pounds, the moment arm of 20 feet. And at the very end, I have the applied couple of minus 2,000. So again, I solve for the moment, and it comes out to be negative 17 kip feet. Same as before. So what does that mean? Yes?
So like to the left of C, those 3 loads, is that like A, B, C?
A,
The
B.
500 pounds.
This is let me do this. This is point C right there.
So it's CDE.
But this is just to the left of C, like a little to the negative side, and this is just to the right of C, just to the positive side. So really what we've moved is here's the left side, so the 500-pound force is on the right-hand free body. And then if I move just to the right of C, you can see the 500-pound force is no longer on the body. So the left side it's there, the right side it's not. And those distances are super, super small, like infinitesimally small. But you notice that as I move from the left side to the right side and pass an applied load, what happens to my moment? Nothing. Let's sum forces in the y direction and see what the shear is on this right-hand side. So now when I sum forces in the y direction, I have my shear force acting up, and I have a half kip force down and a second half kip force down. That's it. So now my shear is equal to 1 kip. So just to the left of C, it was 1.5 kips. Just to the right of C, it's 1 kip. So what is the change in shear as I go past C? I'm going from 1.5 to 1. What's that a change of? That's a change of minus half a kip. And that matches exactly with the applied load, which is also in the negative direction, half a kip. So plant that seed in your memory, and as we go along, we'll see that as you're worried about the variation of shear force as you move from left to right, every time you encounter a point load, your shear will change exactly that amount. So your shear will have a step in it, like a set of stairs. It'll always, if the loads are down, it'll always step down. If the loads are up, it'll step up instantaneously. So what is the shear at C? I don't know. I know just to the left it's 1.5, and just to the right it's 1. I don't know what it is exactly at C. Which one of those is more important? The bigger one. So it doesn't really matter. Okay? Also, just to note that the change in moment was 0. Oh, one more thing. I know it's trivial, but let's go ahead and finish it up. If I sum forces in the x direction for my free body, make sure in equilibrium, all I have again is axial force, so the axial force is 0. So just kind of keep these in mind, and as we move forward, we'll develop a more formal relationship between these things. But that's a good thing to notice and to keep. If you're looking for some way to help you when you're looking at variation of shear force and bending moment, it's really easy when you hit applied forces. The shear changes instantaneously. So, other questions about this? Okay.